Hi everyone. Today we are exploring the fascinating world of sensors and actuators, the building blocks of almost every smart device around us. Sensors detect the changes in environment like temperature or motion, and actuators take the action based on those signals. In this project, we will connect a temperature sensor to LPC1768 microcontroller and see how it responds in real time. By the end of this video, you will have a complete understanding of how the sensors and actuators work together in an embedded system. Let's dive in. First, let's talk about sensors and actuators. Sensors detect physical changes in the environment and convert them into electrical signals. Think of them as eyes and ears of a system. For example, temperature sensors in thermostats, motion sensors in security systems, and light sensors in smart lights. Now let's talk about actuators. Actuators receive electrical signals and perform a physical action. They are the muscles of the system. For examples, motors and servo motors, LEDs and buzzers, fans and solenoids. In our project, the LM35 temperature sensor acts as a sensor, and we can optimally use a fan or an LED or an LCD as an actuator to respond to temperature changes.
So the first thing is, let's understand the basic structure of an embedded system. The basic structure of an embedded system consists of a sensor, an analog to digital converter, a processor or an application specific IC, a digital to analog converter, D2A converter, and then actuator, and then memory. So here, as you can see that your microprocessor or microcontroller is interfaced with sensor, and the output it is going to an actuator. Since a sensor converts any form of energy into electrical signal, it has to be processed by an analog to digital converter, and that digital information is processed by the processor, and it stores the information in the memory, and again when it gives it to the actuator, because it is in the form of a digital form, it has to be converted into analog form for the actuator to respond. So a digital to analog converter is required. Now we will see different types of sensors for understanding. So as I said, sensors are devices which takes in any form of signal into any form of energy into electrical signal. So you have different types of sensors over here: temperature sensor, infrared sensor, ultrasonic sensor, touch sensor, proximity sensor, pressure sensor, level sensor, smoke and gas sensor. Now let's understand the important component or the heart of our embedded system, which is the microprocessor and the microcontroller. So microprocessor is a device in which the CPU is there on the chip, and all the other peripherals like RAM, ROM, input-output port, timer, serial communication ports are present outside of the chip. So that's why you call it as a microprocessor, in which only the CPU is available on the chip. Now when it comes to the another heart of the embedded system, which is microcontroller, here you can see that the CPU and all the input-output devices, input-output ports, RAM, ROM, timer, serial communication port, everything is embedded on the chip itself. So that's why you call it as a microcontroller. Now there are different types of microcontrollers that are available in the market. Now the one which in our project what we are going to use is, we are going to interface a temperature sensor, which is LM35 temperature sensor, with the microcontroller. That what we are going to use is LPC1768 microcontroller. So this is the generalized block diagram of a LPC1768 microcontroller, and here you can see the microprocessor that this LPC1768 uses is ARM Cortex-M3 microprocessor, which is a 32-bit microprocessor, and you can see all the peripherals are embedded. I mean, all the peripherals are interfaced to this particular microprocessor through multi-layer AHB, that is Advanced High Performance Bus Matrix. So you can see different types of peripherals which are interfaced to your microprocessor here, like UART, I2C, CAN, watchdog timer, PWM, 12-bit ADC, and so on. So here now we are going to understand how to interface or how to do the programming of the ADC, because as looking into the basic structure of an embedded system, we are taking the information from the sensor, and the information from the sensor has to be processed to digital for the microprocessor to analyze it. So we have to do the programming of the ADC over here. So what are the different types of ADCs that are available? So you have flash ADC, successive approximation type ADC, dual slope ADC, sigma delta ADC, pipeline ADC, delta ADC and time interleaved ADC. Now the one which we are going to focus on even though we have these many types of ADCs is the successive approximation type ADC. The reason why, because LPC1768 microcontroller uses this successive approximation type of analog to digital converter. Now let's understand, let's analyze the successive approximation type ADC, but before that let's have a quick look at the block that is present over here in this LPC1768 microcontroller. So as I said, LPC uses a successive approximation type ADC, and you have only one ADC block which is present over here. That is, only one block is there, one ADC block is there. It's an 8 input channel ADC. That means you can have, it takes an input from 8 different sources. 8 inputs means the input sources are 8 different inputs. And this means that the microcontroller can take input from 8 different analog sources, but it can convert only one channel at a time. So only one information that it can process at a time, even though it takes an input from 8 different analog sources. And it's a 12-bit ADC, which means that it outputs 12 bits taking one analog input. So that's what this is a generalized overview of the LPC1768 ADC. And as I said, it's a successive approximation type ADC. So let's understand what is this successive approximation type ADC before we go further to understand the programming of the ADC. Now, what is this successive approximation type ADC? Now you can see that this is the block diagram of the successive approximation type ADC, where the input signal, whatever you are giving, is in analog. And that analog information is being sample and hold. It is given to a sample and hold circuit, and then it is given to one of the input of the comparator circuit, and then you have a control circuitry, and the output of which is given to a SAR, which is a successive approximation register, and then you have a digital to analog converter, and output of this digital to analog converter is given to a comparator, another input of the comparator circuit. Now let's understand how this is actually working and how the input voltage is actually converted into the binary output, that is in the form of a digital form. Now let's understand that. Suppose my input signal is about suppose my input information is 11.2 volts. Let's take an input signal which is a continuously changing signal, and since it is being given to a sample and hold circuit, so that particular after the sample and hold circuit, the input information that is being received by the comparator circuit is 11.2 volts. Now, as I said, this is a successive approximation register, which is the successive approximation register, what it does is, so it's a type of register, but it approximates. So initially what it does is, it is being programmed in such a way that it is going to make the most significant bit to be 1. So here only 4 lines are there, so it only makes the most significant bit to be 1. Now it is 1000. So the equivalent value of this 1000 is going to be 8 volts. So this DAC is nothing but your digital to analog converter. It is converting your 1000, which is in digital form, into an analog form. So the reference voltage has to be given accordingly for the digital to analog converter, so that it just converts this digital information into an analog information. So 1000 is now converted into 8 volts. So here you have 4 inputs, right? So it has the information that the V reference information that you have to give is, it's 2 power 4, that has to be equal to 16 volts. So this 1000 is converted into 8 volts. So now your comparator circuit compares your input analog signal with the input from the digital to analog converter. Now if your input signal is greater than that of your the DAC output, then it is going to make the next significant, it is going to retain the previous bit and it is going to make the next bit to be equal to 1. So it is going to retain your previous bit and it is going to now make the next bit to be equal to 1. So it is now 1100. Now since this 1100 is equivalent to 12 volts now, so which the digital to analog converter is going to process it. So it is now going to give the 12 volts information. So this 11.2 is now compared with 12 volts and it is going to check again this here the input signal is less than the DAC output. So what it does is the next time successive approximation register, it is going to make the previous bit 0 and it is going to make the next bit to be equal to 1. So now the equivalent digital analog information of 1010 is going to be 10 volts. So now again the input information and the DAC output information is being compared and now it is checking that your input information is greater than analog information is V input voltage is greater than that of the DAC output. So again what it does is it is going your successive approximation register, it is going to make the previous value, it is going to retain it and it is going to make the next bit to be equal to 1. So it is 1011 which the equivalent value is going to be 11 volts. So now when it is actually comparing, so 11.2 with 11 almost it is equal. So there is nothing more left for the SAR to make the changes for, because it is only a 4 output, it's a 4-bit information only. So this is the output value which it is being sent to the output. So which is the converted value of your 11.2 volts information, because that is why you call it as an approximation type ADC. So because even though you have 11.2 volts, that 0.2 is being approximated to 11 only and it is giving that digital information of that particular analog information. So it is giving 1011 as your digital information. So this is how the successive approximation type ADC is just going to convert your analog information into digital part. Now coming to your LPC1768 microcontroller, you have a successive block of successive approximation type ADC and it is an 8-channel ADC. That means it can take input from 8 different analog sources and it is a 12-bit output type ADC. That means it can output 12 digital outputs corresponding to your analog input. Now let's understand something about the temperature sensor. So temperature sensor that we are going to use here is LM35 sensor. So here you have it's a 3-bit output, it has got 3 output pins. So one is going to be called as VCC, another one is Vout, another one is ground. So this is VCC has to be given to the voltage and ground it has to be grounded, and Vout has to be connected to one of the inputs of the microcontroller. So that I will show it to you now, the interfacing of LM35 with LPC1768. So you are interfacing a temperature sensor LM35 here with your LPC1768 microcontroller. As I said, it has got 3 output pins. So one is called as VCC, that has to be connected to 5 volts, another one is ground, that has to be grounded, and then the Vout pin has to be given to port 0.25 or ADC 0.2. So as I said, you have 8 pins, that is ADC can take the input from 8 different channels, so which are actually designated as ADC 0.0 to ADC 0.7. So because it is taking input from 8 different sources, so it can be given to any of these particular inputs. That is, either you can give it to 0.0 or till 0.7, but they are multiplexed with the other port pins. So before I actually tell you what it is all about, let us understand what is this port pins. So basically LPC1768 has got 5 different GPIO ports. There is general purpose input output ports, which are named as port 0 to port 4, and these ports are used for general purpose input output information. And you can see that there are 5 different general purpose input output ports, and each port has got 32 pins, and it is designated as port 0.0 to port 0.31. So here also for port 1 it is port 1.0 to port 1.31, for port 2 also it is port 2.0 to port 2.31, for port 3 it is port 3.0 to port 3.31, and port 4 has got only 12 pins for its functionality, and you can use it for port 4.0 to port 4.11. So so as I said, this ADC inputs are multiplexed with this port pins. So while interfacing, you can interface to any of the ports, but looking at over here, this port 0.25 is actually interfaced to ADC 0.2 pin. So you are making use of that, and you are interfacing that, you are connecting your LM35 output to this port 0.25 or ADC 0.2 pin. And the ground is also connected to ground, and you are using a Zener diode. It is generally used for an voltage regulator. Whatever the output voltage that is coming out of your LM35 temperature sensor will be regulated, and a constant voltage that spikes will not be there when microcontroller is actually receiving it. So that is the reason for using this Zener diode. So this is the simple interfacing. Now we are going to do the programming of this ADC block. So for that, what you have to do is you have to open the 𝐂𝐫𝐚𝐬𝐢𝐭 version 4. So we are just going to do the programming in 𝐂𝐫𝐚𝐬𝐽 software. So basically this is the overview. I mean, this is when you open, what will happen is you will get a empty, so the software opens, and what you have to do is you have to open file, new Microvision project, and you have to give the file name as So I'm just giving a name as ADC YouTube, and then I'm going to save it. So once I do the saving of it, you can see that you can see the different companies, and you have to click on this NXP founded by Philips. And when you just scroll down, you can see something like LPC1768. You click on it, and you can see the description of it. The LPC1768 consisting of 32-bit ARM Cortex-M3 microcontroller. So and different you can see all the different types of peripherals that it has got internally built in with it, and you can just click OK. So once it says copy NXP LPC1768 startup code to project folder and add file to the project, just say yes. It's asking me to override. Yes, no problem. I'm clicking on yes. So usually that next pop-up will not open for you, but if it opens, you have to just say yes, and just expand this target and expand this source group. You will just see the startup file over here. This is very important. And once you do this, you have to click on, after you do this, you have to click on file, new, and once you do this, you have to start writing the program here. So first thing is I'll just make you understand. The first line is the interfacing of the LM35 sensor to ADC of LPC1768. So this is what we are actually going to do. So what I'll do is I'll just immediately save this file. So I'll just save this particular file. As ADC YouTube. I missed .c, so I'll just click it again and open a new file and save it. Yes. So here is where I'm going to write the program. So I'm going to interface my LM35 temperature sensor to the ADC of LPC1768. So first one, I'm just going to include the header file, so which is #include LPC17XX.h. So I'm just going to include that header file over here. So this is the header file which contains all the LPC17XX registers. Everything is included over here, so we have to include this particular header file. So then we'll just start with my main program. And in the main program, I'll just make use of something which is called as LPC_SE 𝐂𝐫𝐚𝐬. So I'll just make use of this. So this is the first line that I'm writing in my main program, which says LPC_SE 𝐵𝐶𝐬. So what is this 𝐵𝐶𝐬? So in order to understand the LPC1768 registers, you have to download this LPC1768. I'm sorry, I have to download. Yes. So you have to download this LPC1768 manual from the internet. So which contains all the information of this LPC1768 registers. So this 𝐵𝐶𝐬, so what is this 𝐵𝐶𝐬? So let's search over here in this manual which gives the information of what is this 𝐵𝐶𝐬. So 𝐵𝐶𝐬 stands for Power Control for Peripherals Register. So let's see the register configuration of it. Yes, so as I said, 𝐵𝐶𝐬 stands for Power Control for Peripheral Registers. Now here in this, what you're doing is you're making the 12th bit to be equal to 1. So basically here if you check, your 12th bit stands for A to D converter power control bit. So you are basically powering up the ADC, so it is a software control power. So only when you give this bit to be 1, your ADC block will get power. So that is why what you're doing is in the 𝐵𝐶𝐬 register, you are actually making the 12th bit to be equal to 1. So this is the first step in the programming of the ADC. And this LPC_SC, all of that you can find it in this LPC17XX.h. So in this particular SC, that is, again you will just understand what is SC. Okay, so basically SC stands for system clock. So this power control for peripheral register is actually present in that particular system clock register. So that is why this is actually linked to this LPC_SC, because these are all already predefined in this particular header file. So now we have made the first step, that is we have power up the ADC block. So once after we do that, so the next step is to choose the clock selection. So I'll go with 𝐵𝐶𝐬 here. So I'll reopen this file. Okay. So now let's go for this. The next step is you have to choose the clock selection. So what is this clock source select? So now we have to understand what are the different types of clocks that are present in this LPC1768 microcontroller. Now LPC1768 microcontroller has got 3 independent oscillators. So the LPC1768 is being clocked from 3 different oscillators. They are main oscillator, internal RC oscillator and RTC oscillator. So basically you have internal RC oscillator. So internal RC oscillator is going to produce a nominal frequency of 4 megahertz, and you have the main oscillator which can operate from at frequencies of from 1 megahertz to 25 megahertz, and you have an RTC oscillator which provides the clock to mainly to the RTC oscillator, RTC clock. That it is going to provide on from 1 hertz to up to a 32 kilohertz clock. So these are the 3 different types of oscillators that are available in this my LPC1768, from which it is LPC1768 gets the clock. Now we are going to make the clock selection out of these 3. So the clock selection is done by means of selecting the appropriate register. So that register is nothing but this clock source select. So we have to just see this in the manual. So the register is nothing but clock source select. And here you can see that this clock source select register, in which the first 2 bits are only functional and the rest of the bits, that is from 2nd to 31 bits, are actually reserved. And you can see that when you give 0 0, it internally by default selects the RC oscillator as the clock source, and if you give 0 1, it selects the main oscillator. If you give 1 0, it selects the RTC oscillator. If it is 1 1, it is actually reserved. So the value that you have to give here is 0 0 because you are selecting the internal RC oscillator over here, and that is enough for us for powering up for getting the clock. So we don't need a very high oscillator like main oscillator. So that is the reason why we are only choosing the internal RC oscillator. So the next step over here is selecting the peripheral clock. So by means of giving the appropriate value in the P clock select 0 register. Now coming to this P clock select 0, so just look for that in the manual. Now you see that this peripheral clock selection, again you have to give the appropriate selection, because this 25th and 24th bit in this peripheral clock selection 0 register is responsible for peripheral clock selection for the ADC block. So you have to give the clock selection even for the ADC block. So you have to make this if it is 0, so the reset value is 0 0. So let's try to understand by going down. Now what happens is, when you give the value as 0 0, the peripheral gets divided by 4 clock, that is, it is actually getting a C clock divided by 4 value. If it is 0 1, it is actually getting the same value as the C clock. If it is 1 0, it is getting a C clock divided by 2 value, and if it is 1 1, it is getting a C clock divided by 8 value. Now the C clock value that we have now is 4 megahertz. We know that it is nothing but your internal RC oscillator that we have selected. So if you give the value as 0 0, what will happen is this 4 megahertz is getting divided by 4, and 1 megahertz is the one which goes for your ADC block. So ADC does not require a much higher input or much higher clock's frequency. So it is enough if you just it is enough if you just give 1 megahertz clock also for the ADC block. So what you give is, you can just give 0 0, so that let us see what we can give here. 24th block is actually given 1. So we are given 0 1. 0 1 means, so we are taking the same input. Even if you just give divided by, it is your choice again over the information that you wanted to give. You wanted to work on the same clock, or you wanted to work on you wanted to give a less input frequency, that also you can give. So actually here it is selected as 0 1. So that means the 4 megahertz itself is going as a P clock peripheral. So ADC gets 4 megahertz as the input clock for its functions. So so your ADC gets 4 megahertz. So what you're doing here is, you're making 24th bit as 1. So when you make that 24th bit as 1 here, so over here your 24th bit you're making it 1. 1 means the actual C clock is being going for the ADC block itself. So the next one is this. So the next one is, we have to choose the corresponding GPIO port, or I can say the ADC port, ADC pin, the exact ADC pin. So for that you're giving this, which is, you have to see it in the pin select 1 register. So just go and search for that in the pin select 1 register. So here you can see the pin select 1 register. It is actually responsible, this is a 32-bit register. As you can see the different pin names of its particular information. So basically when the function is 0 0, what will happen is, it is basically function like port 0 16 pin or 17 pin or 18 pin, as so on. And when the value is 0 1, it has got some special functions. When it is 1 0, it has got some special functions. When it is 1 1 also, it has got some special functions. So you have to, as you already know, we are just interfacing it to the port 0 25th pin, which is also a special function, ADC second pin. So you have to go and look for the port 0 25th pin, and which is also this ADC second pin. So when you want to make it as ADC second pin, the same port pin, when you want to make it work like an ADC second input pin, you have to make the function as 0 1. That means you have to give the information as 0 1 over here. That means 18th pin you have to make it 1. So that's what we are doing here. 18th pin you're making it 1, so that to make your port general purpose port pin 25th pin, you are making it to act like an ADC port 2 pin. So after this you have to give the corresponding information in the ADCR register. For the ADC to work. Now you check for that in the ADCR register. First, let's see what is this ADCR register. So what is ADCR register? So let's search that in the manual. So the next one is, let's check for the contents what we need to do in the ADCR register, which is the ADC special register. Now here you can see this is your ADCR register, which is nothing but called as A to D control register. And here you can see that you made the 21st bit to be 1 and second bit also to be, you've made it 1. So 21st bit you have to make it 1 only then the ADC A to D converter will be operational. And also second bit you are making it 1, which means you are informing the A to D ADC block which pin you have to sample and hold, because you have 8 input pins. Which is designated as 0 to 7. So now here you have connected as per the PPT I have shown you. Here you are connecting the output of your LM35 with ADC 0.2 pin. So that means you have to inform the ADC block that you have to take the input from the second pin and you have to sample and hold it. So that is why you have to make the corresponding changes in the this ADCR register. So you're making the second bit to be also equal to 1 over here in the program. So that's it. So after this, so till this the initialization, the corresponding changes that you have to make in the for the ADC block. And now whatever the information that the ADC is taking it from the sensor, it is the microprocessor is going to process that and it is going to display that on the LCD. So you have to initialize your LCD first. So what you're going to do here, the initialization part, everything I will explain after completing this ADC part, ADC programming, because without this LCD part you cannot display the content of what the sensor is actually sensing. So here you are just initializing the LCD part. So after making the necessary changes in the ADCR, and first what you have done is you have powered up the ADC block, you have selected the clock oscillator, the internal RC oscillator, and you have selected the what frequency that the ADC block should receive, and you have made the corresponding pin changes in the pin select register. And finally you have made the corresponding changes in the ADCR. Now the program starts here. So what you have to do is you have to inform the ADC to start the conversion. So once you have informed the ADC to start the conversion, it will convert the input analog voltage into its equivalent digital part. So it's while of 1. So every time, so you are continuously doing it. So what you are doing is you are informing the ADC. So here in the ADCR register, you are making the 24th bit to be equal to 1. So go and check in the ADCR register. So here you can see that this 24 to 26 bits, you can see that it is 000 means no start and 001 means start conversion now. So here you are making 001, that means you are making the 24th bit to be equal to 1, which means you are informing the ADC to start the conversion now. So your ADC will start its conversion. After that, so once the ADC has started its conversion, you are checking whether the conversion has happened or not. So that checking whether the ADC has finished the conversion or not, or it is still converting, so that you can check it in the ADDR register. So again you have to go check it in the manual. So ADDR register, I'll just go down and check. So it is there only. It is ADDR is nothing but A to D data register. So this is called as ADDR register, A to D global data register. Now here you are just checking the 31st bit of your ADDR register. Why it is 2 means 2 stands for it is because you have given the input to the second pin of your ADC channel. So that is why it is corresponding to the channel number 2. Now here what you are doing here is you are just checking whether the ADC has finished the conversion or not. So this bit is set to 1 when A to D conversion completes. So if it is not, then it will still be 0. So that is why you are checking if it is 0 or 1. If it is 0, you wait for it, you do nothing. And if it is going to become 1, you extract the result. So it is cleared when this register is read and when the ADCR is written. If the ADCR is written while the conversion is in progress, this bit is set and new conversion is started. So the thing here is this bit will be set when the ADDR conversion is completed. So when it is actually not completed, it will remain at 0. So if it is 0, that means it is you wait for it to become 1. So once it has become 1 and once the conversion has been completed, so you have to extract the result from the A to D block. And where the result will be actually in once the conversion has been completed, the result you can see it in the ADDR register only, in the A to D global data register. The result is available in the 4th to 15 bits. So here you can see that when the done bit is 1, this field contains a binary fraction representing the voltage on the AD0N pin selected by the select field. So this contains the result. So 4 to 15 bits contains the actual result. So now you can see that. So as I said, once the conversion has been completed, so the 4 to 15 bits are the ones which where the results are going to be. So and that is there again in the ADDR register only. So what you are actually doing here is you are just right shifting that by 4 because it is not available. The digital information is not available from 0 to 12 bits. because it's a 12-bit ADC and it is not available from 0 to 12. It is available from 4 to 15. So what you're doing is you right shift that information by 4 bits so that you make it available from 0 to 12, and you just you AND it with FFF. That means you just FFF means you're getting back the original result only, but the important thing that you should do is you extract it, you right shift it by 4 bits and then you AND it with FFF so that you get back your original result, and that you put it in a variable called as result, and that result variable you declare it in main function. So you just declare that result variable in the main function. So I'm just declaring my variable result in the main function. So the digital information is now available in a variable, in an unsigned 32-bit variable that is called as result. Now once after doing that, now my result is available with me, the digital information. Now the thing that you have to understand is whatever the information that I have has to be multiplied, because that is digital information, right? That has to be multiplied by the 𝐕 voltage divided, there is an ADC conversion formula. So that is, so I have the digital information which is available with me. Now that has to be multiplied by 𝐕 divided by, one second. So 𝐕 divided by 2 to the power of n. So n here stands for its a 12-bit, so 2 power 12. So this is nothing but, you call it as a resolution of the ADC. So basically this 𝐕 divided by 2 power 12 is nothing but the resolution of the ADC. So your result has to be multiplied by the resolution of the ADC to get the exact result, digital form of your analog voltage. So your result, whatever you are getting, has to be multiplied by the resolution of the ADC. So now that information, whatever you got, which will be in the form of an voltage. Now whatever the result into the 𝐕 divided by 2 power 12, that means the result multiplied by the resolution of the ADC is nothing but your analog input voltage. It is nothing but your voltage. Now this voltage, whatever you got, has to be again converted into the temperature, because we needed the exact the temperature, the proportional temperature of the voltage that the ADC measures. So ADC has measured the voltage. Now you need to get the temperature related to that particular voltage. Now at LM35, now talking about LM35 outputs for 1 degree Celsius. For 1 degree temperature change, so for 1 degree temperature change, it is going to output voltage change by 10 millivolts. So this is the behavior of the LM35. So you can just check it in the internet as well. And LM35 sensors produces the output voltage change of 10 millivolts per degree Celsius. Now suppose if the room temperature that it is actually measuring is going to be 25 degrees Celsius, then if you multiply that with respect to the voltage, what it will have 25 into 10 millivolts. So that is going to be nothing but 10 divided by 1000, so it is 0.25 volts. So it is 0.25 volts. So this is the voltage that, this is the this is the corresponding voltage that I will be getting. Now if you see, this is the relationship between the voltage and the temperature. So temperature is 25 degrees Celsius, voltage that I got is 0.25 volts, but I don't want 0.25, I want something with respect, I need 25 to get displayed on the LCD. So what I have to do is, so I have to multiply the voltage whatever I have got here into 100. So to bring back the 25, the value as 25. So when I do that, I get the value as 25, and I can easily put this 25 on the LCD. I can just transport this 25 on LCD to understand that 25 is the 25 degrees Celsius. So this is the relationship between the voltage and temperature. So temperature, if it is 25 degrees Celsius, the voltage, the corresponding voltage from the LM35, it is going to be 0.25 volts. Now this 0.25 volts, whatever you got, this is actually got after multiplying your result with 3.3 by 4096, that is with the resolution of the LCD, with the resolution of the ADC, you are getting this particular 0.25 volts. So this 0.25 volts has to be multiplied by 100 to get back your 25 volts. So once you have got that 25, that is why you are multiplying that value by 100. So once you have got that, what you are doing is, I hope you understood this. So I'll just copy. So this is the formula responsible for converting it into the actual temperature to get you the get the actual result. Now after doing this, you're making use of an sprintf function. So what this sprintf function does? So basically it is going to convert your integer into string. So basically this is an integer, so whatever 25, whatever you have got, that is actually in terms of an integer that has to be converted into string. Why? Because your LCD does not understand the integer part, that has to be ASCII coded. So you are converting that integer into its corresponding string value, and you are putting that. So when you just when you just send it to the LCD, or LCD will understand, and it is going to display that particular value back as integer. So that is what you are, that is actually done easily by means of sprintf function. So it is going to convert this particular temperature, so which is in the form of integer, into the form of string. So that string value, again you are using another integer, another variable that is called as stemp. So again stemp has to be declared in the main function, the converted value of temp to stemp. So even temp has to be declared. So I'll just declare these two in the main function. Okay, so what you are doing is, the temp is already a declared function which is containing 25. Now that 25 is converted into a string by means of an sprintf function, and the new variable that is holding the string value is stemp. And here you can see that it is temp is equal to, so how it will get displayed on the LCD is TEMP, which is in the double quotes. So TEMP is equal to percentage of 0.2f. So your information of your temperature will be up to 2 decimal places. So up to 2 decimal places it is going to give you, that is why it is 0.2f. So up to 2 decimal places it will give you the information of your temperature. Then this percentage C, small c, is for 2 to 3. This is again an ASCII coded value. So for displaying the degree, so you wanted degree to be displayed. So in order to do that, you are giving an ASCII information 2 to 3, the corresponding code, and for that you are giving its particular percentage C thing, and then you are giving that C stands for Celsius. So your information that will get displayed on the LCD is temperature is equal to the information like 25.22 degree Celsius. Celsius means C here, so 25 degrees C. So that will get displayed on the LCD. So for that you are writing this particular statement. So at last what you are doing is you are writing that stemp in your LCD string write function, so that the 25 point up to 2 decimal places will get displayed on the LCD. So now it's time to understand the LCD part. Now till then it is all about the ADC programming. So the LCD that we are going to use here is a 2x16 liquid crystal. So LCD stands for liquid crystal display, and whatever the LCD that we are using is a 2x16 LCD. That means it is going to have 2 rows and 16 columns, and it is going to have 16 pins. And these are the 16 pins of the LCD. It is going to have a VSS, VDD, V0, RS stands for register select, RW stands for rewrite, E stands for enable, and the 8 output pin or 8 input pins of the 8 data lines of the LCD, you call it as D0 to D7, and you have an anode and a cathode. So here these are the LCD commands. So once you give these information, the LCD reacts accordingly and it is going to give the respective function. So if you give the value as 01, it will clear the display screen. If you give the value as 06, for example, it is 06, it means it is going to enter into the entry mode, and it is going to receive the information. And if you give the value as 28, it is going to work like 4-bit 2-line 5x7 dots. Then if you give the information as 08, it is going to work like display off and cursor is also off. 0C for display on and cursor off. And 80 for forcing the cursor to the beginning of the first line. C0 stands for forcing the cursor to the beginning of the second line. So accordingly now we have to give the commands. So to make your LCD act like whether it has to be in an 8-bit mode or 4-bit mode. Basically we can make use of all the 8-bit modes. At a time LCD can receive all the 8-bit of information, so you don't want to go for 4-bit information. So accordingly you give the information as 38, which is function set 8-bit, and 2 lines, so both the lines it will make use, and each information is available as 5x7 dots. That means each digit will be displayed as 5 rows and 7 columns. So these are the codes which are responsible for making the LCD to function. And this is the interfacing of your LCD with LPC1768. So the interfacing is pretty simple. As you can see that port 0.15 to port 0.22, you are connecting to the D0 to D7 lines of the LCD, and 5 volts to 5 volts, ground to ground, and port 0.10 is actually connected to register select pin, and port 0.11 is actually connected to the enable pin. So this is how you are actually giving the connection, and there is an LED, that is A and K. A is connected to 5 volts and K is connected to grounded, and V0 is actually connected to a variable potentiometer. This is basically used for contrast adjustment. So this V0 is actually used for contrast adjustment of the LCD. This is the simple and a very easy interfacing of LCD with LPC1768. Now let's start working on the program. It will be interesting now. So the first thing that you have to work on is LCD command write. Okay, we'll start with LCD initialization function. So in the LCD initialization function, I'll just take another news text and save it first. So in the LCD initialization function, I am making use of FIO DIR register. So basically, what is this FIO DIR register? So to understand that, I'll just explain you. Fine, so we have created the hex file corresponding to this C file, that is ADC YouTube and LCD95.c. Now we need to dump it into the board that we have. So basically this is we just have to dump it into the microcontroller which is there on our board. The board name is LPC1768 development board version 2.0. So first what I am doing here is I am just opening a software that is called as a FlashMagic version 5.87. so you can download it from the internet, and here you are selecting the device which is LPC1768, and the COM port that is again dependent on the device manager. Anyway, for mine it is going to be it's COM4, and baud rate is 9600, and oscillator it is I'm giving it as 12 megahertz. And hex file, you have to browse and check it as, yeah, so this is YouTube hex file, right, which is, you have to imagine ADC YouTube. Oh, just check what is the name of the have to check for ADC YouTube. Yes, so it is ADC YouTube. So your Microvision name, that is the project name ADC YouTube, and the hex file name should be the same. So you have to just click on that and say it open. Now once you have done that, you have to just click it as verify after programming. Then you have to check it off. If it is not checked, then you have to just click on start. Unable to communicate, that means there is a COM port problem. So that means you have to just check it in the device manager. So check for the COM ports. Under COM ports you are seeing it's COM6. So you have to select COM6 here and then start. So it's attempting to connect, that means your COM port is correct. So fail to auto board, that means you have to just reconnect your board again clearly with the cable. You reconnect the cable to the board, and then once again, yeah, it's programming, that means it is correct. So yes, now you can see that it is finished. So the dumping has happened. So now you can see the display of the temperature, which is 28.76 or 29.25. So its little variation will be there as the temperature variations of the room will keep on changing. So you can see the display of the temperature on the LCD. So this is the temperature sensor, which is LM35. So you can see here, this is the temperature sensor which is LM35, and you can see it is actually connected to 0.25 or ADC 0. Which is again the alternate function is going to be ADC 0.2 as explained in the program. So here you can see the display, and that's all about this programming of ADC.